welcome to this problem walkthrough. Today, we'll be diving into the problem titled Pizza with 3 in slices. This is a fascinating challenge that involves dynamic programming and optimization techniques. Let's explore the problem together and break it down step by step. In this problem, we are working with a circular pizza that has been sliced into exactly 3 in pieces. Each slice has a specific size, represented in an array called slices. Your task is to select exactly n slices from this pizza, but there are 2 key constraints. First, no 2 selected slices can be adjacent to each other in the circular array. Second, you need to maximize the total size of the slices you choose. The input to the problem is the slices array, which contains the sizes of each slice, and you are guaranteed that the length of this array is always a multiple of 3, meaning it will always be 3n. The output is a single integer, which represents the maximum sum of the sizes of the n slices you select while adhering to these constraints. Let's look at a concrete example to understand this problem better. Suppose the input array slices is 1, 2, 3, 4, 5, 6. Since the pizza has 6 slices and the length of the array is 3n, we know that n equals 2, so we need to select exactly 2 slices. However, we also need to make sure that the slices we pick are not adjacent in the circular array. In this case, the optimal choice is to pick slices 4 and 6. These 2 slices are not adjacent, and their sizes add up to 10. Therefore, the output for this example is 10. This demonstrates how the constraints of adjacency and maximizing the sum come into play. Let's explore another example. Here, the input array is 8, 9, 8, 6, 1, 1. Once again, the pizza has 6 slices, which means n equals 2, so we need to select 2 slices while ensuring they are not adjacent. The best choice here is to pick the 2 slices with sizes 8 and 8. These slices are not adjacent, and their sum is 16, which is the maximum we can achieve under the given constraints. For the output, we would return 16. Now consider a slightly larger example where the input array is 4, 1, 2, 5, 8, 3, 1, 9, 7. The pizza has 9 slices, so n equals 3. This time, we need to select 3 slices, again making sure no 2 are adjacent. The optimal solution here is to pick the slices 4, 8, and 9. These are not adjacent, and their sizes add up to 21, which is the maximum possible sum. So the output for this example is 21. To summarize the key constraints and edge cases for this problem, the length of the slices array is always a multiple of 3, meaning it will always be 3n. The value of n can range from 1 to 500, and the size of each slice, represented by slices, I, is always between 1 and 10,000. Let's also consider a few edge cases. In the smallest possible input, where the pizza has just 3 slices, for example, 1, 2, 3, n equals 1, and you need to select just 1 slice. In this case, the output will simply be the largest slice, which is 3. Another edge case is when all slices are equal, such as 5, 5, 5, 5, 5, 5. Here, the output will be the sum of any 3 slices, which is 15. Finally, for large inputs, such as when slices contains 1500 elements and n equals 500, the solution must handle this efficiently without running into performance issues. To begin, let's consider the brute force approach. The idea here is to enumerate all possible combinations of n slices from the given 3 in slices in a circular array. Since no 2 selected slices can be adjacent, we would need to ensure that all subsets generated adhere to this adjacency constraint. For each valid subset, we calculate the sum of the selected slices and determine the maximum sum. While this method is conceptually simple and easy to implement, the trade-offs make it impractical. The number of subsets we need to evaluate grows exponentially as the size of n increases, leading to extremely high computational costs. This approach does not leverage the inherent structure of the problem, making it infeasible for larger inputs. Next, we move to a dynamic programming solution for a simplified version of the problem, where we treat the array as linear instead of circular. The goal is to maximize the sum of selected slices while ensuring no 2 selected slices are adjacent. To achieve this, we use a dynamic programming approach where dp, I, j, represents the maximum sum obtainable from the first I slices by selecting exactly j slices. For each slice, we have 2 options: include the slice, which adds its value to the sum and skips the next slice, or exclude the slice and move to the previous one. This logic is captured in the recurrence relation, dp I, j equals max, dp I2, j1, plus slices, I, dp I1, j. While this approach handles the linear case efficiently with a complexity of O n squared, it does not directly address the circular dependency of the array. Now, to account for the circular nature of the problem, we refine our dynamic programming approach. In a circular array, selecting the first slice means the last slice cannot be selected, and vice versa. To handle this, we break the problem into two subproblems. In the first subproblem, we exclude the first slice and consider slices from index 1 to 3 and 1. In the second subproblem, we exclude the last slice and consider slices from index 0 to 3 and 2. For each of these cases, we apply the same DP approach used in the linear version, and the result is the maximum value obtained from the two subproblems. By solving each subproblem independently and taking the maximum, we effectively handle the circular dependency while maintaining a time complexity of O n squared. This approach balances efficiency with the added complexity of solving two linear DP problems. Ultimately, the chosen strategy is the dynamic programming approach with circular arrays. The key insight here is that breaking the circular dependency into two linear subproblems simplifies the logic significantly while preserving the problem structure. The recurrence relation ensures the sum is maximized while adhering to the adjacency constraint. This method achieves an optimal balance between complexity and efficiency, with a feasible O n squared time complexity for the problem constraints. Unlike the brute force approach, it handles the circular dependency effectively, and while it is slightly more complex to implement than the linear DP approach, this added complexity is necessary to address the circular structure. Overall, this strategy is both scalable and optimal, making it the ideal solution for this problem. In this problem, we are tasked with selecting n slices from a circular array of 3 n slices in such a way that no two selected slices are adjacent, and the total sum of the selected slices is maximized. The circular nature of the array adds complexity because the first and last elements are adjacent, which makes it impossible to directly apply a linear selection strategy. To simplify the problem, we break it into two linear subproblems. The first subproblem considers the array excluding the first element, while the second excludes the last element. By solving these two subproblems separately, we can eliminate the circular constraint and focus solely on the adjacency restrictions. Once we have the results of both subproblems, the final solution will be the maximum of the two results. To solve each of the linear subproblems, we use a dynamic programming approach. The idea is to compute the maximum sum we can achieve by selecting exactly j slices from the first I slices of the array, while ensuring that no two adjacent slices are selected. To define the state, we use dp I, j, where dp I, j represents the maximum sum achievable with the first I slices in j selected slices. The state transitions are as follows: if we select the current slice, the previous slice cannot be included, which leads to the formula dp I, j equals dp I2, j1, plus slices, I1. If we do not select the current slice, the state is inherited from the previous computation, dp I, j equals dp I1, j. Combining these cases, the state update becomes dp I, j equals max, dp I1, j, dp I2, j1, plus slices, I1. This transition ensures that we account for both possibilities, selecting or skipping the current slice, while maintaining the adjacency constraint. To implement the dynamic programming solution, we start by defining the base cases. If no slices are selected, the sum is 0, so dp 0, 0 equals 0. If we attempt to select more slices than available, the result is impossible, which we handle by setting dp 0, j equals inf4j greater than 0. Additionally, if we opt to select 0 slices, the sum remains 0 for all I, so dp I, 0 equals 0. Once the base cases are established, we iteratively compute the dp table using the state transitions. At the end of this process, the result for the linear case is stored in dp m n, where m is the number of slices in the subproblem. To account for the circular nature of the original problem, we solve the two subproblems separately. For the array excluding the first element, the result is dp m n. Similarly, for the array excluding the last element, the result is also stored in dp m n. Finally, the maximum of these two results gives us the solution to the original circular problem. The key insight in solving this problem is breaking the circular constraint by splitting the array into two linear subproblems. This transformation allows us to leverage dynamic programming to efficiently handle the non-adjacency constraint. Another important optimization involves reducing the space complexity of the DP table. Instead of maintaining a full 2D table, we can store only the last two rows of the table, as the state transitions depend only on these rows. This reduces the space complexity from O(n) squared to O(n). Additionally, the algorithm accounts for edge cases, such as arrays with minimal input size, 3n equals 3, all negative elements, where the result should be 0, and all positive elements, where the algorithm should correctly identify the maximum sum. For large values of n, the algorithm remains efficient by avoiding unnecessary computations and focusing only on valid transitions in the DP table. The use of optimized data structures ensures scalability while maintaining correctness. The time complexity of this algorithm is O(3n*n), as we iterate through all 3n slices and compute the DP state's 4n slices in each subproblem. The space complexity, with optimization, is reduced to O(n), since we only store the last two rows of the DP table during computation. By breaking the circular dependency and solving two linear subproblems, we effectively reduce the problem complexity while ensuring correctness. The dynamic programming approach handles the adjacency constraint efficiently, and space optimization makes the solution scalable. This approach not only guarantees the maximum sum of non-adjacent slices but also ensures that the algorithm performs well across various edge cases, making it a robust and efficient solution to the problem. This solution addresses LeetCode problem number 1388, pizza with 3n slices. The problem involves selecting n slices from a circular array of 3n slices to maximize their sum without selecting adjacent slices. ###explanation. 1. Circular dependency handling. The circular nature of the problem means the first and last slices cannot both be selected. To handle this, the problem is split into two scenarios. Exclude the last slice and solve for the first n slices. Exclude the first slice and solve for the remainder. The result is the maximum value from these two scenarios. 2. Dynamic programming subproblem. The helper function calculate_max_sum uses dynamic programming to solve the subproblem of selecting n non-adjacent slices from a linear array. A DP table is used where dp, I, j, represents the maximum sum obtainable by considering the first I slices and selecting j slices. 3. State transition. For each slice I and count j. Either exclude the current slice, inheriting the value from dp, I1, j. Or include it, adding its value to the best sum possible by selecting j1 slices from the first I2 slices, dp, I2, j1. The recurrence relation is dp, I, j equals max, dp, I1, j, dp, I2, j1, plus ar, I1. 4. Base cases. When no slices are selected, the sum is 0, dp, I, 0, equals 0. When the array is empty, the sum is also 0. 5. Final calculation. The helper function is invoked twice to calculate the maximum sum for each scenario, excluding the first or last slice. The result is the maximum of these two values. This approach ensures an optimal solution by leveraging dynamic programming, and its complexity is O(n) squared, where n is the number of slices in each subproblem, 1/3 of the total slices. Here, we start with the Java implementation of the solution to the pizza with 3n slices problem. The main method, maxSizeSlices, is designed to find the maximum sum of slices we can pick, adhering to the rules of the problem. To achieve this, we define a helper method called calculateMaxSum, which takes an array and a parameter n, the number of slices we are allowed to select. This method uses a dynamic programming approach. A two-dimensional array dp is created, where dp, I, j, represents the maximum sum we can achieve by selecting j slices from the first I elements of the array. For each slice, we have two options: either exclude it and inherit the previous maximum sum, or include it, which adds its value to the best result from two positions prior, since consecutive slices cannot be picked. Once the table is filled, the maximum sum is stored in dp, len, n. Using this helper method, we address the circular nature of the pizza slices by considering two cases, excluding the first slice or excluding the last slice. These are handled using the arrays.copyOfRange function to create subarrays that omit the necessary slice. For each case, we calculate the maximum sum using the calculateMaxSum method. The final result is the maximum of the two computed values, ensuring we account for all valid combinations. This implementation balances clarity and efficiency, leveraging dynamic programming to solve the problem within the given constraints. In this problem, we are tasked with selecting slices from a circular pizza with 3 slices in such a way that the sum of the selected slice sizes is maximized. However, the circular nature of the pizza imposes a restriction: no two selected slices can be adjacent. This makes the problem more complex than a standard selection problem. To solve this, we use dynamic programming. The circular constraint is addressed by breaking the problem into two cases. In the first case, we exclude the first slice, allowing us to consider slices from the second to the last. In the second case, we exclude the last slice, so we consider slices from the first to the second to last. By calculating the maximum sum for each of these cases and taking the larger result, we effectively handle the circular constraint while ensuring no adjacent slices are chosen. Let's walk through an example with the array of slices 1, 2, 3, 4, 5, 6, where n equals 2. First, we calculate the maximum sum in the scenario where the last slice is excluded. This means we work with the array 1, 2, 3, 4, 5. We initialize a dynamic programming table DP with 6 rows and 3 columns, representing the array length +1 and the number of slices to select +1, respectively. Then, we fill the table iteratively. For instance, at I equals 1 and j equals 1, the value is the maximum of not taking the current slice or taking it, resulting in dp 1, 1 equals 1. Similarly, at I equals 3 and j equals 2, we compare excluding the current slice with the sum of the current slice and the best result from 2 steps back, yielding dp 3, 2 equals 4. After filling the table, the maximum sum for this case is dp 5, 2 equals 8. Next, we repeat the process for the scenario where the first slice is excluded, working with the array 2, 3, 4, 5, 6. The final result for this case is dp 5, 2 equals 9. Comparing the two cases, the maximum sum is 9. Now consider a second example where the slices are 8, 9, 8, 6, 1, 1, and n remains 2. For the first case, we exclude the last slice and use the array 8, 9, 8, 6, 1. Using the same dynamic programming approach, we fill the dp table. The final result for this case is dp 5, 2 equals 17. For the second case, we exclude the first slice and use the array 9, 8, 6, 1, 1. After completing the calculations, the final result is dp 5, 2 equals 15. Comparing the results of the two cases, the maximum sum is 17. This demonstrates how the dynamic programming approach efficiently handles different configurations of the problem, ensuring that the circular constraint is respected and the optimal solution is found. Finally, in a third example, we use the array 4, 1, 2, 5, 8, 3, 1, 9, 7 with n equal to 3. In the first case, we exclude the last slice, working with 4, 1, 2, 5, 8, 3, 1, 9. After filling the dp table, the maximum sum for this case is dp 8, 3 equals 21. In the second case, we exclude the first slice, using 1, 2, 5, 8, 3, 1, 9, 7. The result for this case is dp 8, 3 equals 22. Comparing the two scenarios, the maximum sum is 22. This concludes the example and highlights the power of dynamic programming in solving this problem. By breaking the circular constraint into two linear cases and using a systematic approach to calculate the maximum sum, we ensure an optimal solution. The time complexity of this approach is O(n squared, due to the nested loops, while the space complexity is also O(n squared, for the dp table. To analyze the time complexity of this problem, we start by breaking it into its components. First, the outer function, maxSizeSlices, is invoked twice, once for the subarray slices, :1, and once for slices, 1. Since each subarray has a length of len, slices, 1, we can denote the length of the full array as m, where n equals m/3. Each call to max size slices processes an array of size M1. Within this, the key computation happens in the calculate_max_sum function. This inner function uses dynamic programming and constructs a 2D DP table of size, len, r, plus 1 x, n plus 1. The outer loop runs for len, r, plus 1, which equals m iterations, and the inner loop runs for n plus 1, or approximately m/3 plus 1. Each operation inside the inner loop, such as calculating the maximum and performing additions, has a constant time complexity of O1. Combining these, the time complexity of calculate_max_sum is O, m*n, or equivalently O, m*m/3, which simplifies to O, m²/3. Now, looking at the total time complexity of the solution, since the calculate_max_sum function is called twice within max size slices, the combined time complexity becomes 2 O, m²/3. Simplifying further and dropping constants, we arrive at an overall time complexity of O, m². Next, for space complexity, the primary contributor is the dynamic programming table. This DP table has dimensions, len, r, plus 1, x, n plus 1, which translates to mx, m/3 plus 1. Therefore, the space usage of the DP table is O, m*m/3, or O, m²/3. Aside from the DP table, the input array slices takes up O, m, space, and any additional memory usage, such as recursive stack space, is negligible. Thus, the dominant factor in space complexity is the DP table. The total space complexity of the solution is dominated by the DP table, which requires O, m²/3, space. When we drop constants, this simplifies to O, m². Comparing this dynamic programming approach to a brute force solution highlights the efficiency of this method. A naive approach would involve generating all possible subsets of size n from the input array while ensuring that no adjacent slices are chosen. Since generating subsets is combinatorial, it would have a time complexity of O, 2 to the power of m, with additional overhead for checking validity. This results in exponential time complexity, which is impractical for large inputs. In contrast, the dynamic programming approach reduces this exponential complexity to O, m², by leveraging overlapping subproblems and using a 2D table to store intermediate results. Furthermore, the best, average, and worst-case time complexities are all O, m², as the same steps are followed for any valid input. To solidify our understanding, let's break down the mathematical reasoning behind the big O complexities. The calculate_max_sum function involves two nested loops. The outer loop runs for m iterations, and the inner loop runs for n equals m/3 iterations. Multiplying these, the total number of operations is O, m*m/3, which simplifies to O, m²/3. Since this function is called twice, the total time complexity becomes O, m². On the space side, the DP table, which has dimensions mx, m/3, dominates the space usage, resulting in a space complexity of O, m²/3. Dropping constants, this simplifies to O, m², as well. In conclusion, the dynamic programming approach offers a significant improvement over the brute force method, achieving both time and space complexities of O, m², making it highly efficient for this problem. Now, let's talk about some common mistakes students often make when solving this problem. One of the biggest pitfalls is using non-optimal subarray selection methods, such as attempting to brute force all possible subsets of size n. While this approach might seem straightforward, it fails to account for the constraint that selected slices must be non-adjacent, leading to unnecessary computations. This brute force method has an exponential time complexity of O, 3 to the power of n, making it impractical for larger inputs. Another frequent mistake is forgetting the circular nature of the pizza slices. When this happens, solutions often include both the first and last slices, which violates the problem's adjacency constraints. Additionally, some implementations struggle with overlapping subproblems in dynamic programming. Without proper memoization or state management, these solutions may either recompute the same subproblems multiple times or produce incorrect results. This increases the time complexity and can make the solution inefficient. Another mistake to watch out for is misunderstanding the problem constraints. Selecting more or fewer slices than specified can lead to invalid solutions and missed edge cases during testing. This is especially important in scenarios where edge cases involve small arrays or specific constraints. Index out-of-bounds errors are also common in problems involving circular arrays. These errors typically stem from off-by-one mistakes or invalid index accesses when implementing dynamic programming or iterative solutions. Such mistakes can result in runtime exceptions or undefined behavior. From an interview perspective, it's crucial to recognize that this problem is closely related to the house robber 2 problem. While the circular constraint adds complexity, the core idea of maximizing non-adjacent selections remains the same. The optimal approach involves using dynamic programming with 2 runs, one excluding the first slice and another excluding the last, to respect the circular nature of the array. Always be prepared to handle edge cases, such as when n equals 1 or all slices have the same value, and be ready to explain why simpler methods like brute force are inefficient compared to the O(n) dynamic programming approach. This problem is also connected to several related problems that you might encounter on LeetCode. For example, House Robber 2 introduces the circular array constraint for non-adjacent selections, while House Robber is a simpler version without the circular constraint. Another related problem is delete and earn, which involves maximizing values under specific constraints, and minimum swaps to make subsequences increasing, where dynamic programming and careful state management are also key. In terms of alternative approaches, a naive greedy method might involve always selecting the largest slices without considering adjacency constraints. While this is fast to implement, it doesn't guarantee an optimal solution since it often violates the problem's rules. A more advanced approach is dynamic programming with space optimization. Instead of maintaining a full DP table, you can use just 2 variables to track the previous and current maximum values. This is more space efficient, though it requires careful bookkeeping to avoid errors. Finally, recursive solutions with memoization explicitly handle subproblems and store results to avoid redundant computations. While this approach is easier to implement, it can have higher memory overhead compared to iterative dynamic programming. Each method has its trade-offs, so it's important to choose the one that best balances efficiency and simplicity for your needs. Great job on completing this problem. To summarize, we use dynamic programming to handle the circular nature of the array and maximize the sum of selected slices. We also discussed the importance of state representation and optimization. Thank you for watching, and don't forget to like and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!